Hello everyone, my name is Kathan and today we'll be discussing the problem bit strings from the introductory problems of the CSES problem set. Let's begin. Alright, so here's the question. A task is to calculate the number of bit strings of length n. What is a bit string? A string which has only 0 and 1s in it. For example, if n equals to 3, the correct answer is 8 because the possible bit strings are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So these are the 8 possible bit strings we have if n is 3. What is a bit string again? A string which has only zeros and ones in it. Our input is very simple, an integer n which goes from 1 to 1e6. Fine. And they are asking to print the result modulo 1e9 plus 7. So this is also a very common thing in competitive programming. What happens is sometimes the result cannot be fit into a largest possible integer as well. So but they have to verify the answer somewhere, some way, right? So that's why they ask you to print the result modulo 1e9 plus 7. We'll touch upon this, what this actually means and why this is needed in the explanation part, but I'm just giving you a heads up that we have to print result modulo 1e9 plus 7. All in all, the question asks just output me number of bit strings of length n, right? All the possible number, like what does that count? How many number of bit strings you can create if I give you an integer n in range 1 to 1e6. It says answer can be very large, so give me a modulo 1e9 plus 7. Example input is 3 and 8, so these are the bit strings. So they don't ask you to print the actual bit strings, but just the count of bit strings. Fine, so I guess that's about the question. Let's go to the iPad and try to dry run some test cases and then we can approach this question. First things first, let's go through some test cases here. So for n equals to 2, what do you think should be the answer? So what are all the possible bit strings here? So first one is 0, 0, then we have 0, 1, then 1, 0, 1, 1. So here what do we output is, we have to output 4, right? Because there are 4 possible bit strings here, right? So 1, 2, 3, 4. Then for n equals to 3, we have 8 possible bit strings. So what were those? It was actually given the question itself, right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And if we are observing, what I'm doing is I'm effectively listing down all the binary numbers from 0, 1, 2, 3, so on and so forth. So I hope you know a little bit about binary numbers because I think if I discuss binary numbers here, then it will make the video unnecessarily long. So just a little bit about binary numbers, right? So how do you convert from decimal to binary and all would be helpful here. Fine. So this is 0. Okay, this is 3. Then I'll write 4. Then 1, 0, 1, 1, 1, 0, which is 6, and 1, 1, 1. So effectively, how many bit strings are there? So these are all the possible bit strings, which turns out to be 8. So this 8 is what we have to return. Fine. How do you approach this question? This question can be approached using just fundamental rules of counting, right? So I hope you have studied in your +2 somewhere like permutation combinations, right? So just basic, okay, nothing much. Fundamental rules of counting, right? So addition law and multiplication law. So what you have is effectively you have n places to fill, 1, 2, 3, 4, so on. We have n positions to fill, and in each position we have two options, 0, 1, 0, 1, 0, 1. Why? Because we have to form a bit string. So for each of the position we have two options to fill with. That is, here you have two ways. So 2 ways to fill the 0th, like in the first position, 2 ways to fill the second position, 2 ways to fill this position, and so on, right? So effectively you have 2 ways to fill each and every position. Now what do we want to find here? We want to fill all the positions, right? So your answer will be what? It will be 2 into 2 into 2 into why? Because we have to fill all the positions one by one. So 2 into 2 n times. So our answer turns out to be 2 power n. Why? Because we have n positions to fill, and for each position we have two possible options, either put 0 or 1, and we have to fill all the positions. So one by one we have to fill. So if you remember that OR and AND concept, we have to fill the first position and second position and the third position, so on, right? So when we have AND, we multiply. That's why 2 into 2 into 2, so on, n times, so it's 2 power n. So this question is very simple then, right? So the code, like the pseudo code, if I write, it will be very simple. I equals to 1 to n. You can maybe initialize the result here to 1, right? We just need to calculate 2 power n. So it will be result star equals to 2, and you'll be happy, right? But wait, you cannot do this directly. Why? Because this 2 power n can be very large. They have specifically mentioned in the question that you have to print whatever the answer is modulo that big number, right? So it was 10 power 9 plus 7. So I can write it like 10 power 9 plus 7, or in short I usually write it like this, 1e9 plus 7, or let's just call this guy as m. This m represents the number which you have to mod with. So why they're asking for this and not just 2 power n? They could have easily asked you, right? Now this relies in the fundamental thing that sometimes you cannot store the answer. So this is not limited to this question. There are a lot of questions where you cannot store the answer in the maximum integer you can have. So I'll show you why. So here, like, the question is done and dusted, right? So all you have to do is you have to calculate 2 power n, because this represents the count of all the possible bit strings. But this number cannot be stored in a integer, or you can say unsigned long also, which I'll show you. See, what happens is the n's range is n can be as high as 10 power 6 or 1e6. So 2 power n can be as high as 2 power 10 by 6, right? So this, if you know what is the largest number that you can have, the largest number you will get will be from unsigned long, right? The largest number that you can store will be from unsigned long, which turns out to be somewhere 10 power 36. Now how do you convert this 10 power 36 to 2's power? Because I want to check whether this number is less than 10 power 36 or not. So if you want to convert a 10 power to 2's power, I guess we already discussed in the, you can say, the first video of this playlist. You just divide this number by 3 and multiply it by 10. Right, so effectively what you'll get is it will be 2 power 2 power 120, right? So like 3 12s are 36, so 2 power 120. So unsigned long's maximum range here is 2 power 120. And what is this 2 power 10 power 6? Whatever it is, I know for the fact that this value is definitely greater than 120, so you cannot store it even in unsigned long as well. So since you cannot store it unsigned long, what you do is you just find out mod m, where m is 1e9 plus 7. Mod has an interesting property that whenever you mod a number by, let's say, 5, the output. So what is this mod operation? It just divide by the number, whatever remainder you get. So the output will always lie in range here 0 to 4, right? So whenever you mod by number m, the output will always lie in 0 to m minus 1, right? So this, since 1e9 plus 7 is actually an integer, the output can be stored in an integer. So that's why they're asking for mod, right? So I guess you are clear about why we actually need to perform mod, right? So if you are clear why this modulus operation is needed, please write understood in the comment section. And you should be having one question now. If I am not able to store 2 power n in integer, how am I gonna calculate 2 power n mod m? Right? You might say, right, to calculate this value also I need this 2 power n. So how am I gonna do that? So that's when we have to see some fundamental properties of this modulus operation. So what this modulus operation has is it has some fundamental properties which helps you to simplify this even as well. Fine. So the problem is clear, right? So you want to find out 2 power n mod m, but the problem is this number cannot be stored in an integer or even unsigned long, the highest positive integer that you can get. So how can I calculate this entity? I know this entity is less than you can say 1e9 plus 7, that is, it fits very well within integer range, but this thing is not. So how can I do it? Let's just go through the properties of modulus. So the property of modulus is, if you have, let's say, a into b mod m, there is this fundamental property of mod that it can be equal to a mod m multiplied by b mod m entire multiplied by mod m, right? So this is the fundamental property of mod. So if you want to see, I can give an example here. Let's say we have 7 into 5 and we are modding it with let's say some 2 guy, right? Say 2. So this is as good as, so what is this? This 35 mod 2. 35 mod 2 will be 1, right? 35 is odd number, so this thing is 1. But you can also write it like 7 mod 2 into 5 mod 2 mod 2. So this turns out to be 7 mod 2 will be 1, right? And 5 mod 2 will also be 1. and 1 into 1 mod 2, which actually gives you again 1, right? So this can be verified, like you can put some numbers and verify, but like this is a fundamental property of modulus, that if you have a into b mod m, it can be written as a mod m into b mod m mod m. So why this helps is, I'll show you. Let's say you are multiplying a chain of numbers a, b, c, d, right? You are multiplying this chain of numbers mod m, right? The problem here can be that this entire thing can be very big, right? And you may not be able to store it. So what you can do is, you can exploit the property of mod. What you can do, you can consider this part as one number, let's say n1, and this part is another number n2, right? And you know that from the fact n1 into n2 mod m can be written as n1 mod m into n2 mod m whole mod m, right? Whole mod m, right? So this property you can exploit. So effectively this can be written as a into b into c, a into b into c mod m into d mod m whole mod m, right? Similarly, this thing can be broken as well, right? So this thing you can write like a into b mod m. So effectively what I'm doing is, you are treating you are treating this guy as same and this guy as different. So a into b mod m into c mod m whole mod m, right? And this, like you already know, a mod m, b mod m, mod m. So effectively, if you want to calculate here 2 power n, which is 2 into 2 into 2 into so on n times mod m, this question can be written like 2 into 2 mod m, right, into 2 mod m into 2 mod m, so on and so forth, right? So final will be mod m, right? You might say, Kathan, okay, there should be a mod m here as well, but 2 is less than 1e9 plus 7, right? So there's also one more property, that if let's say k, if we have k mod m and this k is less than m, then answer is simply k, right? So this is also like 2 mod 5 is 2, 3 mod 10 is 3 if k is less than m. So that's why I'm not writing here 2 mod m, right? 2 mod m internally, because that guy is anyway less than m. So effectively, to calculate 2 power n, what you can do is, you can just multiply 2 into 2, then take it with mod, then you multiply with 2 and again take mod. So you can sequentially take mod, and it will effectively calculate the total answer mod m. Now the beauty of this approach is, you will never cross the highest, you can say highest limit, which is what we calculated, 10 power 36, right? Why? Because you're always bounding the number by m, right? So this result will always be less than m. This result, like this result will always be less than m, right? Similarly, this result here also will take mod, right? It will always be less than m. So you will never be out of range. So that problem is solved, right? So you don't have to actually calculate a number which is greater than unsigned long long. Fine. So effectively our strategy becomes, for I equals to 1 till n, what you have to do is, you can initialize the result to 1. Now you have to do result equals to result into 2 mod m, right? So you may think, you may say, Kathan, write here mod m, but it's not needed. Why? Because 2 is less than 1e9 plus 7, so that result will be anyway 2. And this result also will not cross 1e9 plus 7. Why? Because see, you first multiply it with 2, then take again mod. Right? So this result is also ensured to be less than m. That's why after this you can just print result and your job is done. Right? So I hope you got it, right? If you got it, please comment understood right now. And what is the time complexity? Can you tell me? You are just going one time throughout the loop, right? So the time complexity will be simply order of n. And yeah, I mean, this can be easily implemented, right? So the pseudocode itself is the code. You just ensure that this result is a long long or unsigned long long, just for safety. And since we know that n can only be as high as 10 power 6, an order of n loop will work, because you can do somewhere like 1 power, like 10 power 7 to 10 power 8 number of operations in 1 second. So that works. But I want to give a bit more and show you an even more optimal solution to find this, like find the 2 power n, or in general I want to show you a way to find a power b more optimally. So you can say the most optimum way possible. Now the naive way here is to simply, like, if you want to calculate a power b, or in this case 2 power n, what you will do is you will run a loop for this b number of times, right? So for I equals to 1 till b, and you will have a result which is 1, and you're just gonna multiply result equals to a, right? You're gonna multiply a b number of times. So this is the most naive way, and this runs in, you can say, the order of b here more of concretely, where b being the power that you're trying to raise. Fine. So can we do better than this? And turns out we can. And the answer lies in this special algorithm that you will hear a lot in competitive programming, which is called binary exponentiation. The name looks daunting, but it's actually a very simple idea. I would like to show you, like, how would you yourself come up with the idea of this binary exponentiation, right? So let's say I have to calculate 3 power 16. I'll take two examples. One is of even power and one is of odd power, and it will give you some idea of what you're trying to do. And let's say I want to calculate one more power, which is let's say 3 power 15, right? One even power, one odd power. Now to calculate 3 power 16, one approach is the naive approach, just go from 1 to 16, multiply 316 number of times. But here you can clearly see, instead of doing that all hassle, you can just multiply 3 power 8 with 3 power 8. Now to find 3 power 8, one approach is you just go from 1 to 8 and just compute 3 power 8. Or you can just find 3 power 4 and multiply it with 3 power 4. Can't you do it? For calculating 3 power 4, one way is just go from 1 to 4 and calculate 3 power 4. But wouldn't the simple thing would be just calculate 3 power 2 and multiply it with 3 power 2. And this 3 power 2, like, it is simple, right? It's just 3 into 3. So fine, so that's 3 power 2. So this you can clearly see, instead of going 16, you can say, like, running a loop for 16 times, what you've effectively done is you have just calculated 3 power 8, 3 power 4, 3 power 2 and 3 power 1. Right, so this automatically gives you a hint. From 16 you went to 8, from 8 to 4 to 2. So this gives you a sense of some log n base 2, right? So this is what happens in, you can say, when number gets divided again and again by 2. You'll get it, don't worry. So let's say for 3 power 15, what do you have to do? Now this 3 power 15, of course you cannot break it like 3 power 8 into 8 because it's not even power, but you definitely know that this 3 power 15 is actually 3 into 3 power 14, right? This 14 can be broken now. Instead of going from 1 to 14, you just find 3 power 7. You just find 3 power 7 and multiply it with 3 power 7, right? 3 power 7. Now it definitely cannot be, like, you can go from 1 to 7 and you cannot break it like that, but it definitely can be written as 3 into 3 power 6. This 3 power 6 can be now further broken. That is, you just calculate 3 power 3 and multiply it with itself, right? 3 cube can be written as 3 into 3 square. 3 square, we already know it's 3 into 3, right? So just to take 3 and multiply it with 3. Fine. So if I want to write a function here, a recursive function to does this, so you can easily implement it, right? So it's a recursive function. For 3 power 16, you need 3 power 8. For 3 power 8, you need 3 power 4. For example, in 3 power 15, what you need is, you need 3 power 7, right? You need 3 power 7, or more precisely, you need a value of 3 power 6, because if you have 3 power 6, you can calculate 3 power 7. Then for 3 power 6, you need a value of 3 cube. Precisely, you need a value of 3 square, because you have 3 square, you can just multiply it with 3 and you get 3 cube. So effectively, if I want to write a function here, power AB, the first thing that we need here is the recursive function. I need power of AB by 2. Why? See, to calculate 16, I need 3 power 8 so that I can multiply it with itself, right? To calculate 3 power 8, I need 3 power 4. To calculate 3 power 15, the first thing that I need is 3 power 7, which is actually 15 by 2. Why? Because if I have 3 power 7, I can multiply it with 3 power 7, I'll get 3 power 14 and I can multiply it with 3, right? So That's what I'll need. For example, to calculate 3 power 7, what I'll need is I'll need 3 power 3, because if I have 3 power 3, I'll multiply with 3 power 3, I'll get 3 power 6, and I can multiply with 3 and get 3 power 7. Right, so all in all, I'll need this value first, a power b by 2. Fine. And now, maybe I can write a different color. If this b is even, that is, the power is even. In this case, if let's say it's 16, you just multiply 3 power 8 with 3 power 8. So in this case, just return result into result. So we want, this is the case, right? Or else, so this is the case where b is odd. So this is the case, right? So it is the case here. So if you get 3 power 7 back, what you have to do is you have to do 3 power 7 to 3 power 7. You get 3 power 14, and you have to multiply it with 3, right? So in this case, this is what you have to do, right? So here you will return a into result into result. So this can be, you can say 3 power 7 to 3 power 7 and one more time 3, right? So that's what it is. For example, if you want to calculate this 3 power 7, you will need 3 power 3, but the output will be what? The output will be 3 power 10 into 3 power 3 into 3, right? So power of 3 power 7 will be 3 into 3 by 6, right? 3 power 6. That's why you have to do this. Only one thing remains, how would you stop this recursion, right? This recursion will stop when you will have the smallest possible value of input, which is this 3 power 1, right? So here the base condition will be pretty straightforward. It will be that if b is equal to 1, you just have to return what? What do you return when power is 1? It's simply a, right? So a power 1 is 1, 3 power 1 is 1 here. So I mean, that's the, you can say, the implementation of this logic, right? So what is the time complexity here? Effectively, you are going like this. You have b, then you go and calculate b by 2, then you go and calculate b by 4, or you can say b2 square, and this goes on until this b2 power k becomes 1, right? So at some point this power will vanish, right? So this becomes 1. So it will stop when b is actually equal to 2 power k, and what will be this? This k is actually the number of steps, right? So here it's first step, second step, so on and so forth. So this k will actually be, if you take log both sides, k will be equal to log b. So this loop and this recursive function, the time complexity is log b. Why? Because in each step you are doing just constant operation, right? So this runs for log b number of times, and here every time we only have some constant operation. So this is the constant operation that we have, and this thing will be called log b number of times by this logic. So the time complexity here is log b base 2. Fine. So yeah, I mean, this is optimal solution, right? So this can be implemented, right? Whatever we want. So if we want a modulus everywhere, so we will have modems here, we will have modems here, and so on and so forth, right? So that's, you can have a mod here. So wherever you are not sure, you can have mod, or simply just follow the property of mod. Wherever there is a chance that the result will be greater than m, you just take mod. So that's binary exponentiation, the recursive version. But in practice, we don't use a recursive version. We have an iterative implementation, which again I'll explain you with an example. Let's say I have to calculate 3 power 10. Now what is the obsession with this 3s? Not really, you can have any number. What matters is I'll take one odd power and one even power to make you understand what is happening here. If you look at this 10's binary, it will look something like this, 1 0 1 0. So this is actually base 2 representation, okay? So this 10 is in decimal representation. Now what happens here is this 0 is actually at 2 power 0 position. This is actually at 2 power 1 position. This is 2 power 2 position. This is 2 power 3 position. It is same as in decimal. You have this first place as units, which is 10 power 0. Then this is tens, 10 power 1, hundreds, thousands. So same way in binary also you have 2 power 0, 2 power 1, 2 power 2, 2 power 3, so on and so forth. Right. Now what does this see? Like if you just see here, this 3 power 10 can actually be written as 3 power 8 plus 3 power 2. 3 power 8 plus 3 power 2. This is how it can be written as, right? And this 3 power 8 plus 2 turns out to be 3 power 8 into 3 power 2, right? Let me write one more. Let's say we have 3 power you can say 13. What is the binary of 13? 13's binary is looking like 1 1, which is 8 plus 4 12, and we'll have one more here. Let me go again to little bit detail. So this is 2 power 0, this is 2 power 1, 2 power 2, 2 power 3. So this again can be written as 3 power 8 plus 2 power 2, which is 4, plus 1, which is 2 power 0. So again, this can be written as 3 power 8 into 3 power 4 into 3 power 1. If you look closely, what is happening here is to get a power b, what you effectively do is just multiply a power 2 power k if b's kth bit is set, right? What effectively did is, this is 0th bit, first bit, second bit, third bit, 0th bit, first bit, second bit, third bit. If you want to find 3 power b, what you do is you just multiply 3 power a power 2k where kth bit is set, that is first bit is set, you take 3 square, 3 into 2 power 1, that is third bit is set, you just multiply 3 into 2 power 3 here. Which bits are set? Third bit, sorry, so here third bit, second bit, 0th bit. So 3 power 2 power 3, 3 power 2 square, 3 power 2 power 0, right? So to get a power b, you just multiply a 2 power k where kth bit of b is set. So that is the idea, and this is the approach. So why do you think this also will be log b? Because if you have a number n in decimal representation, if you convert in binary, it's gonna consume log n number of bits. So this is like a fact of binary numbers. If you convert a decimal number n, let's say this was in a base 10, and you convert to a binary number, it will take a log n number of bits. So if you have a number b in a decimal, it will have log b number of bits. So effectively, we'll never be doing more than log b number of multiplications here, right? Because you don't have more than log b number of numbers here, like the bits. So the time complexity turns out to be log b base 2. Fine. And about the implementation, let me just show you the implementation, then we can go through a dry run. This looks scary, but it's not. First things first, I'm just modding it with the mod, for the reasons that this a can be, you can say, very big, let's say 118, then you have to do it. But since a is very small here, this is not needed. Otherwise, I'm just initializing a result with 1. I'm initializing my result with 1. Right, so this will be the 2 power n mod m that I want to calculate, and I will be initializing a with a, right? So a is a, fine. So fine. And let's just say we have to calculate 3 power 10. So this b, this is a binary representation of 10 that we just saw. And let's say I want to calculate 3 power 10. What I'm going to do? Well, b greater than 0, which is indeed greater than 0. First, I'm going to check. So this b and bitwise and 1 is, you just check whether the, you can say, the first bit, you can say the 0th bit is set or not. So rest all will be 0 here. So b and 1. If this bit is set, this is going to return some value. This is going to return 1, right? So this condition will be true if the 0th bit is set or not. Is the 0th bit set? No, the 0th bit is not set. So that means you don't have to multiply with 3 into 2 power 0, right? That's what it means. So you don't have to multiply it with 3 power 0. So yeah, result is untouched. But for next time, if this bit is set, you will have to multiply it to 3 into 2 power k, right? So for that, you just multiply 3 with 3, right? Multiply 3 power 1 and 3 power 1. So it becomes 3 power 2. Fine. Now how do you move to the next bit? You just right shift the number by 1, right? So this scary looking thing is nothing. This is just B right shift equals to 1. So I'm just right shifting everything by 1. So effectively the number now becomes like this. Now is B greater than 0? Yes, it is still greater than 0. Now is the 0th bit set? So effectively 0th bit here will be the first bit. So this thing is just asking the question whether the kth bit is set or not, right? Is the first bit set? Yes, definitely. So that means multiply with 3 into 2 power k, right? So that's why I'm going to multiply result with 3 into 2 power k. So it becomes 3 square, right? Now we can right shift afterwards, but before that, if the second bit is set, I'll have to multiply with what? 3 into 2 power 2, that is 3 power 4. So multiply a with a, that is 3 power 2 into 3 power 2. That becomes 3 power 4, right? For the next time, if the second bit is set, we'll have to multiply into 3 into 2 power 2, which is 3 power 4. Fine. Now again, is b greater than 0? Yes, still it is. But is this bit set? B and 1? No. So b and 1 means you put 1 here, all 0. So it is greater than, will this like satisfy to true? No, it won't be. So we move ahead, we right shift, but before right shift, for the next guy, we might have to multiply into 3 into 2 power 3. So just multiply a with a again. So now this will become 3 power 8. And finally, will be here. So this is what? Now, is this bit set? Yes, this bit is definitely set. So you multiply with what? 3 into 10 power 8. So you multiply it with 3 into 10 power 8. Right? And after that, you have to multiply. If there was some bit, you will have to convert it into 3 power 16. Why? Because if there was a fourth bit here, you may have to multiply into 3 into 2 power 4, which is 16. So that's why you may have to multiply into 3 power 8 here. But yeah, and after that, if you come here, now b will become 0 and this loop won't be executed. Effectively in result, you will have stored 3 into 2 in 3 power 2 into 3 power 8, which is 3 power 10, right? So this is simple, right? So this loop runs again. You can say effectively you are just going through all the bits in the binary representation of b. So this loop will just run order of log b based on number of times, and every time you are just doing a constant operation. So in this order of log b, you are finding a power b. So if you want to find 2 power n, you just plug in 2 here and n here, and it also calculates the mod part. And if this mod wasn't clear, this is required when a is very high, when a is in range 118, because if you don't perform a mod here, this multiplication can cause overflow, right? So this multiplication causes overflow, right? A into a. That's why this mod is required here. Fine. And I guess that's pretty much about it. So I hope you understood the binary exponentiation, both recursive and iterative version. And let's wrap up this video by looking at the code. But before that, please comment understood if you have followed the video till now. It will actually make me happy that okay, I think the explanation was good enough. And let's go to the code then. Okay, so here's the code. The naive implementation, which is very simple. You just have a loop from 1 to n. And here's the implementation for optimized version of binary exponentiation, right? So I have just initialized the result to 1. Then while b is greater than 0, so effectively you are going through each bits of b. If b and 1, if the first bit is set, should I say here, you can say if the kth bit is set. That's what effectively this guy is checking, right? So not first bit. If the kth bit is set, you just multiply with whatever a into 2 power k, right? So this a at that moment will be a into 2 power k, and you take mod with it. Fine. Otherwise, you just figure out what will be the next a power 2 power k, right? And you just right shift by 1. And you just return the result. Here I am ensuring every time whenever I do multiplication, I take mod here so that I don't cause the overflow. And like the question can be very simple now. You just take input n, and answer, if you don't forget, is actually 2 power n, right? So whatever function you can use, any one of them will work. I have not written here recursive version because that is your job. Please write the recursive version in the comment section, and I'll maybe give you a thumbs up there if it's correct or not. And yeah, I mean that's that about this video. I hope you enjoyed the detailed breakdown of the naive version and the binary exponentiation as well. Fine, then I'll see you in the next one.